Hello. I'm hoping that you are having a great start to your weekend. We are going to go over this working with numbers notes. They are fill in the blank. You will need to fill them out in your packet to be checked on Monday. So take a moment, if you need to, pause the video, get out your packet, and turn to this page. We're going to start with number 1. It says mathematics uses positive and negative whole numbers as well as fractions. This is a little bit different because in science we usually deal with really large or really small quantities, and so instead of putting them in fraction form, we will use decimals. So, for example, we use scientific notation, if you remember. So we use numbers like 6.02 times 10 to the 23rd to represent a certain number. So this is obviously a very large number. 10 to the 23rd would make it extremely large. So we're going to use scientific notation for that instead of just writing it out. That's where it's important to use decimals instead of fractions. In math, you usually are dealing with relationship between numbers. So you're looking for a relationship. If your instance for us is looking at 4 minus x equals 2, you're looking for that relationship between 4 and 2. In science, however, we are dealing with the relationship between quantities. Now, as we've discussed earlier, quantities are just a number of whatever object or stuff that you are looking at. So they sound similar, but they are not. A quantity is going to be a measured unit value. So this unit part here refers to somehow you've measured it with some tool, and you're going to define what tool that is using units. This means that it's really important that we never have any naked numbers. So we want to make sure that every single number that we have has a unit connected to it. In math, variables are abstractions. Okay? They don't have any physical interpretations. Sometimes we talk about having 4 apples and 3 oranges, but really those numbers are just numbers. They're ideas. And so when we talk about x1 or y equals mx plus b, there where your m is your slope, you're really just talking about the idea of those numbers. They don't actually represent anything in the physical world. However, in science, variables often refer to specific physical entities. So they're referring to actual things. So, for example, we did volume and mass with our soda lab, and we'll see that this y equals mx plus b, if we use that same equation, in this case, even so m is still your slope, the slope actually represents something or idea, and that thing or idea is then the density of what you are looking at. Mathematicians often deal with exact numbers. So they are looking for very precise amounts. So like if you have 3, you know 3 is an exact number. Scientists, we are not so sure. We're working with uncertain measurements. And we talked about uncertainty a little bit when we talked about what we had in our graduated cylinders. So we're looking more and more at how do we know the number the best we can. Usually we don't. All measurements are going to have 3 parts. Okay. They are going to provide a number, a unit, and they're going to tell you about the uncertainty. We talked a little bit about uncertainty today, but we're going to go a little bit in depth here. So our example that we talked about was measuring those graduate cylinders. So if you are telling me that you got 20 milliliters of your sample, and you're not sure because it's kind of stuck between two little lines there, and you're not quite sure where it is, you're going to give it plus or minus 0.05 milliliters. Okay, so this means that you know for sure this is your number here. Here is your unit, and this is your degree of uncertainty. You're not quite sure if it's up a little bit or down a little bit away from this here. Okay. Your uncertainty is also going to change. So this looks like a very precise instrument here. We know this to the hundredths. But if we use, say, 100 graduated cylinder, say this is a burette, which we will talk about later. Say we're using a 100 milliliter cylinder. Instead of having this 0.05 degree of uncertainty, well, this is a little bit bigger, it's a little less certain, so we're probably only going to be able to know this number as good as the half milliliter. So as you can see, even though our unit stays the same, our uncertainty is a little bit greater. We're not as sure about this number as we were here. Some of the sources of that uncertainty, why we might not know how certain a number is the first thing we talked about up here, this burette and the cylinder, is limitations of the tool. So every meter stick is a copy of the standard meter. Is this tool professional or student quality? So some things are very precisely measured and very precisely created. Other things are not. So if you're using maybe a plastic beaker, it might be a little bit less precise than, say, a glass beaker because there's a different quality there. Judgment and skill of the operator also factor in, just like we did in our activities. Some students got 95.2 milliliters and some students got 95.5 milliliters. Even if you're looking at the exact same thing, two people might come to a very different conclusion based on what they can see. And then lastly, the conditions in which the tool is used. Sometimes difficult situations increase uncertainties, such as if you are driving in the snow and you know that you can fit your car in a certain parking spot, but because of the snow and the ice in the parking lot, you think, well, you're just going to skip this spot today and you're going to go park in a different corner of the parking lot. In order to get rid of that uncertainty in measurements, so this is also known as increasing the confidence, you want to increase precision. Okay, precision, we will talk about in a little bit, is if multiple measurements are made, they give similar results, then uncertainty is decreased. So smaller units per increment lead to greater precision. So if I have a target here, and I'm throwing or shooting my arrows at it, or I'm throwing darts at it, precision is throwing multiple darts and then landing in the same spot. So if I am precise with my throwing, I might end up with a dart there, a dart there, a dart there, a dart there, but I will not end up with any of them right here. So this is precise. Accuracy, on the other hand, if you're comparing your measurement to an accepted value, so if you might be in the position where you already know what the accepted value should be. For instance, on Friday we got the density of the marble, so we should have an accepted value because we know what the density of glass should be. Then we will also chuck our work so that we get towards that accuracy. So again, if I use that dart analogy, I'm going to take my dart model here, and I'm throwing darts at it or arrows, and I'm going to be starting to hit that target closer to where I need to be. Now, I might start way over here, but as I do more trials, I'm going to get closer and closer to where I actually need to be. Notice that precision and accuracy aren't the same. So this precision, I would never have a dot right out here. Accuracy, I would never be over in another part of the circle. So they're different, but if you have precision and accuracy, that means that you are hitting that bullseye every single time. So you're really doing a good job of getting them to where they need to go. All right. Most of the time, we just understand that no matter what we do, there's always going to be just a little bit of uncertainty. It doesn't matter how good your tools are, there's always just going to be a little bit of uncertainty. We call that the uncertainty range. So every tool has an uncertainty range that's written as plus or minus, and this blank is whatever that might be. So sometimes it's plus or minus 3 units, plus or minus 10 units. Whatever it is, it's going to tell you. Okay. For example, if a mass measurement is given at 88.50 plus or minus 0.05 grams, then the certain value might range from 88.45 grams, the very minimum. So if you take 88.50 and subtract this, you would get 88.45, to 88.55, which is the maximum. So if you take this 88.50 and add this, that's your maximum. So your range of correct answers can be anywhere between this 88.45 and 88.55. So if the actual measurement is 88.48, you wouldn't know that because your degree of uncertainty wouldn't allow you to get that precise. Okay? Uncertainty values are always something given by the manufacturer. If not, use this class rule. So in class, we don't always have access to those manufacturer's notes, so we're going to use this class rule. Uncertainty is equal to plus or minus 1/2 the smallest division on the tools. So we're going to look at some common tools that we have here in the classroom, and we're going to talk about uncertainty. So, for instance, we have a meter stick or a ruler. I'm sure some of you are very familiar with that. And we also have 2 graduated cylinders here. So you will definitely be exposed to those. You've already used those in the classroom. So we're going to talk about those first. Okay, so we had a 100 graduated cylinder. We talked about in class how we're going to find that there are either 10 spaces or 10 lines in between here. The difference between 60 and 50 is 10. So we're going to divide that by the 10 spaces. Notice there's milliliters, should be all over the place because we don't do naked numbers. So we're dividing that by 10 spaces, so that's going to give us 1 milliliter per line. Okay, so then we are going to go 1, 2, 3, 4, 5, 6. So we can start out with approximately 56, and then if we take a really close look, so now we are using plus or minus 1/2 of the smallest division. This smallest division here is 1 milliliter, so 1/2 times 1 milliliter is equal to 0.5 milliliters. So now we can take a look at this. Our greatest uncertainty is roughly giving us this 56.0 milliliters. And that's how we can determine the uncertainty of this graduated cylinder.